The goal is to accurately simulate and/or test the amount of heat the components housed inside the accumulator produce under plausible operating conditions. A cooling system will then be designed that would be fitted to AER's 2020 car. In this video, you can see the various components that were used to assemble our accumulator housing. Within this housing, 84 lithium-ion battery packs were arranged such that 8 packs would be in parallel and 84 would be in series.
In order to visualize the flow across the 6 channels of our accumulator container, we built a model in SOLIDWORKS flow simulation. For our boundary conditions, we used an inlet mass flow rate, representing our pump, and a static outlet pressure, representing the bath pressure of the system. The arrows moving across the graph represent the flow trajectories of the coolant fluid, and given by their distribution, it can be seen that the mass flow rate between all 6 channels is near equal.
Our small-scale test is a circuit composed of a pump, flow meter, radiator, and a small-scale housing of a singular battery pack. 10 variable resistors are hooked up to the battery pack in order to discharge the battery at a reasonable rate. 2 Arduinos are used in order to record the temperature of the AC-110 dielectric cooling fluid using 3 thermistors set up at the exit of the radiator, the exit of the battery, and the exit and after the pump. These Arduinos are able to collect data from the flow meter and the battery temp sensor connected to the battery. The data that is collected from this experiment are used to determine the cooling capabilities of our design and to size our radiator and pump.
For the manufacturing process, we decided to outsource the majority of the cutting and welding to Consolidated Metal Fabrication. You can see in this video that Consolidated Metal Fabrication is using Trump laser to cut the 4130 steel to produce the sidewall of the accumulator housing. They go on to cut the rest of the material needed to move on to welding.